Hello and welcome to this video. In this video we're going to look at some real-life applications of centripetal forces and circular motion. I'm going to choose these specific examples because these will show up most in exam questions, which means you'll be better prepared when you actually enter the exam and are faced with a question like this. So most of the things that undergo circular motion, as we've spoken about before, will be things like on the road. Like we said before, we said that if we go on a roundabout or we're turning a sharp corner that's has some sort of circular path, you'll end up moving in a circular path, so you have some centripetal force. So we'll start with that example. Then we're going to move on to look at a fairground is another common example. They tend to look at like doing a loop on a track or in a Ferris wheel or something like that, and also looking at kind of large swing type things, or just getting down at the bottom of a loop would be the same kind of expression. So we'll look at those. But let's first look at cars on a road. So there are two main examples that will come up quite a lot. The first one is if you're on top of a hill. And so if we were to go over a hill that were to look something like this, obviously this is not like realistic at all, but hypothetically, let's say we had a perfectly circular semicircle of a hill with some radius r to the distance being the distance from the center of this hill to the surface of the hill. Then as we come up and around, at some point it's going to be at the very top of this hill. So we have the car at the very top with some mass m. Now we know from our definition of centripetal force that we could write this as mv squared over r, or we could write it as m omega squared r. For the purpose of this video, I'm just going to take this expression. It's an arbitrary choice. I could have easily taken m omega squared r and they will give me the same expressions, just switching between these two. But I'm just going to go with this one because it's going to make a little bit easier, and this is probably a more common expression. Okay, the other thing that we know is this force is a vector. Centripetal force always has to point towards the center of the circle, and it's also a resultant force. So it means that this force is built up of other forces, and then we need to solve for those forces and look at how we get this whole resultant force here. So if we take the case of a car on a hill, and we look at the forces that are present on this car, one of the most obvious forces is going to be the weight force that's going to come straight down. But we're also going to get some sort of force that's acting up. And I'm going to call this S, this support force. It's almost like the reaction force, but it's not just going to be due to the reaction force. So S is going to be a combination of the reaction force and a few other forces. For example, your force due to a change in momentum, since you're going up and you're gonna invoke a change in momentum vertically, you have to have some force applied there. That's going to be taken into S. And what this means is, since we know our overall force has to point towards the center, that means the weight force has to be bigger than S. So that means mg minus S must be the correct expression for the centripetal force. So this would be an example equation for resolving forces on top of a hill. A second example that we could take is looking at a roundabout. So if we scroll down here for a second and we look at how motion affects on a roundabout, let's say we have, this is the center of the roundabout, and we have some path here. Let's say we have some car here that's moving around in this direction, where the center, the distance to the center of the circle to the car is r, so the radius of the circular path. And in this case, the forces that are acting on this car is only friction. There's only forces. If you were to observe from an outsider's perspective and look at a car going around a roundabout, you'd only see it driving towards the center of the circle. So you only see the force of friction that is keeping it here, which I'm just going to call small f. Okay, and that means that small f in this case must be equal to mv squared over r, or m omega squared r. Okay, now Some of you might be thinking, well, when you're in a car going around a roundabout, you actually move inside the car and you don't move towards the center of the circle, you move towards the outside of the circle. And that's because of a force called centrifugal force. Now, if you mention centrifugal force to any physics teacher, they will tell you that it doesn't exist. That's because it's referred to as a fictitious force. This is why I'm not including this in this diagram. So while there will be forces if you're inside the car, if you're looking from an outsider's perspective, that force doesn't actually exist. This is what's known as a fictitious force, so it depends on the frame of reference that you're observing this from. And this is kind of the whole idea of Einstein's special relativity, which we're not going to get into unless you guys are doing turning points. So for this, we can basically say from an outsider's point of view, there is no force that's going outwards, so all of the centripetal force is purely down to the frictional force. Now, those of you doing maths will then take this a little bit further, and you'll see that actually you'll have a maximum velocity that this car can go around this roundabout with before it slips and slides off the circular path. But in physics, we don't really need to know too much about that. So you guys doing maths can refer to those videos in order to understand that. But for now, we get a nice, easy expression for this frictional force as just the frictional force is the centripetal force. And now we can go on to the second type of examples, which are looking more at the fairground type of rides. So let's look at a roller coaster. So that would be an example, because there's lots of bends and turns in a roller coaster, so you're following circular path quite often. So we can actually kind of condense all of these different points. So you're going to have points where you're going to be at the bottom of a loop, you're going to have points where you might be at the top of the loop, and so on. Okay, if you find the car at the bottom of the loop here, we'll go through this example. If you find the car at the top of a loop here, this is actually going to be the same as going over a hill in a car, so we won't go over this example, but we will look at the fact in the case of undergoing like a full loop on a roller coaster. You have both of these situations. So you have it when you're at the bottom of the loop, and you also have it when you're at the top of the loop. So we're going to look at both of these situations, but I'm going to draw separate diagrams just to make sure that they're both clear by themselves. So let's first look at what happens when we're at the bottom of a loop. So we have a cart here. This is the center of the circle. It has some radius r. This car has mass m, and we can label the forces that are acting on it as mg coming down, and we have that support force that we mentioned before going up. And in this case, since we know the force has to travel towards the center, we can actually say the overall force is S minus mg is going to be equal to mv squared over r. So that would be your expression at the bottom of a dip. And you could probably work out the velocity for this. They'll probably give you the height that you start at, and you could work out your velocity pretty easily by just doing the fact that if you're falling from some sort of height into this loop, then half mv squared should be equal to mgh. Therefore, you can equate that v is going to be root 2gh. So you could probably put that in there and then solve most of those equations like that. But for now, we're just going to say that we could write an expression that looks like this for when you reach the bottom of a loop. Now, if we were to then look at how would it look if we reach the top of the loop, we're then going to have the same radius because it's gone from the same loop. But now when the car is at the top of the loop, we end up with all of the forces acting downwards, because we have, if it's mass m, we have the weight force acting downwards, mg, and the support force is also acting downwards because it's the force that the rail applies to the car, and the car is going to gain that because it's going to go in the same direction. Therefore, in the case when you reach the top, it's actually mg plus s is going to be equal to mv squared over r. Okay, so these are the most common 4 examples that you'll see, and you'll probably see that they're always going to be the same sort of method to work out what your expression is. You always just try and simplify the drawing a little bit to just do a free body diagram, and then label all the forces that are acting. make sure you know that the centripetal force goes towards the center. Take the difference between the forces, or sum of the forces, set it equal to mv squared over r, or m omega squared r, and you'll get your expression to solve that situation. Now I will say, but just before this video ends, that there is a strong link between circular motion and gravitational fields, and you will also, I'm actually going to say gravitational and magnetic fields, since this will be in both of them. But all of the derivations that you need to know concerning the magnetic and the gravitational fields I will do in those videos. So for now I'm just laying down the groundwork of all of these, of the idea of circular motion, and in the videos on gravitational and magnetic fields I'll do the examples of things in orbits, or charged particles moving in circles and that kind of thing. Thank you for watching.